Wave speed and Doppler effect. In this presentation, you will learn the factors that affect the speed of a wave. You will also learn how to calculate the speed of a wave using its frequency and wavelength. You will learn how the observed frequency of a wave changes when the source of the wave moves. The speed of a wave is the number of meters a single cycle travels per second. You can find the speed of a wave by multiplying the frequency of the wave by its wavelength. This makes sense when you review what each of these wave characteristics mean. Wavelength is the number of meters per cycle, and frequency is the number of cycles per second. When you multiply meters per second times cycles per second, you get meters per second. In order to determine the relationship between frequency and wavelength, we need to separate the variables. When we do this, we see that frequency and wavelength have an inverse relationship. When the frequency is high, the wavelength is small, and when the frequency is small, the wavelength is large. There is an inverse relationship between frequency and wavelength. It produces the following plot. The speed of a wave depends upon the material through which the wave travels. If a material is heavy, it tends to be slower, and if a material is rigid, it tends to be faster. Here is an example of a simple velocity question. In this problem, we're told the velocity of the wave is 30 meters per second, and its wavelength is 5 meters. We simply put the information into the equation, and we find that the frequency of this wave is 6 hertz. Here is a more challenging velocity problem. We are given the wave's velocity and asked for the wavelength. We are not given the frequency, but need to find it. We are told that a cork moves up and down 4 times in 8 seconds. We can use this information to find the frequency. If it moves up and down 4 times in 8 seconds, that's 4 cycles per 8 seconds. That's 0.5 cycles per second, or 0.5 hertz. A wave is traveling with a speed of 3 meters per second towards point P, as shown in the diagram. If 3 crests pass by point P in 1 second, what is the wavelength? So this is a question where you get the velocity and you want the wavelength. So clearly you use the velocity formula. Since 3 cycles pass by a point in 1 second, that means the frequency is 3 cycles per second. So we use this frequency, 3 cycles per second, and we use the velocity to calculate the wavelength. You're given a wave with a frequency of 40 hertz, and you want to find the velocity. But what you don't have is the wavelength. But you do know that 2 wave cycles have a length of 3 meters. So a wavelength is the length of 1 cycle. So we take the 3 meters and divide it by 2, and we get a wavelength of 1.5 meters, and plug this information into the velocity formula. In this problem, we're told the velocity of a wave is 20 meters per second. The period is 5 seconds. Period, however, is not in the velocity formula, so we can change period to frequency using the equation frequency is 1 over period. The frequency turns out to be 0.2 hertz, and the wavelength is 100 meters. We've all had the experience of seeing lightning and then a couple of seconds later hearing the thunder. This comes from the fact that velocity's speed in air is 3.3 times 10 to the second meters per second. Now this is found on page 1 of your reference table. The velocity of light, however, is 3 times 10 to the 8th meters per second, making it almost 1,000,000 times faster. Remember both these numbers on page 1 of your reference table. It is very important for you to remember which wave characteristics are determined by the source of the wave and which wave characteristics are determined by the medium. The way that you remember this is simply by memorizing that speed and wavelength are determined by the medium of the wave. That is, they're determined by the material through which the wave travels. If you just remember those two are determined by the medium, you remember everything else is determined by the source. The phenomena that you just heard is called the Doppler effect. You notice when the train is coming towards us, obviously the sound and the volume gets louder, and when it leaves, the sound gets quieter. But what I want you to focus on is the fact that the frequency of the sound increases as it comes towards us, and the frequency of the sound is reduced as it goes away from us. Is reduced as it goes away from us. Hopefully these two pictures will help you understand why there's a frequency change when the source of a wave is coming towards an observer and another frequency change when it's going away from the observer. You take a look at the stationary ambulance and you can see that the sound comes out of the top of the truck and the frequency on the right is equal to the frequency on the left. Now take a look at the second picture where the ambulance is moving to the left. The frequency on the left is higher than the frequency on the right because the truck is actually moving into the last wave that it created and moving away from the last wave it created on the right. The Doppler effect is the variation in the observed frequency of a wave when there is relative motion between the source of a wave and the receiver. A, B, C, or D, which way is the source of this object moving? The answer is B. The Doppler effect is used in radar guns. When the policeman points his radar gun at a car coming towards him, the waves bounce off the car and come back with a high frequency. And when he or she points his radar gun at a car going away from him, the car will bounce off the car with a lower frequency. This frequency shift is used to calculate the speed.